Good morning, everybody. My name is Peter McGrade. I'm one of the Drive and MCC specialists with Turtle and Hughes, and I'll be your presenter this morning. Despite the fact that drives like the 1336, 36 Plus, and Plus 2, they've been obsolete for quite a while. As a matter of fact, the 1336 Plus 2, which was the last of the 36s, has been obsolete since 2010. And there's still a good number of them out there. And what I hope to accomplish today is to give you some motivation or a reason to start on your migration path, and at least give you one reason to start planning it now. The good news is that if you already have a 750 series drive, this feature is available to you to be used at your whenever you're ready. Okay, so we're going to cover predictive maintenance this morning. So why should you use predictive maintenance? One thing is it'll make your life easier and help avoid unscheduled downtime. According to a 2015 survey, it was estimated that $20 billion per year was spent in unscheduled downtime. And it broke down to 8% of those dollars figuring it out if there really was a problem, meaning, thank you, hold on a second, slides aren't moving. Bear with me a moment, experiencing technical difficulties. Try closing it and opening it again. Okay. Bear with me. If you haven't figured it out, this is my first webinar. And let's see if this does it. Oh, there we go. Look at that. So as I was saying, sorry about that, folks. So according to a 2015 survey, $20 billion was lost in unscheduled downtime. And that's a big number. And it kind of broke down to where 8% of those dollars was just figuring out if there was a real problem. Meaning, did an operator hit an e-stop? Did somebody inadvertently walk through a light curtain and shut the system down? Those kinds of issues. When those weren't the issues, there was 21% of additional dollars spent diagnosing the problem, figuring out why the machine shut down. And then 47% of those dollars was spent finding the resources in order to fix the problem, meaning getting the right people in place, getting the tools, getting the parts, getting everything lined up. And if you add all that up, it comes to 76%, which is just slightly north of $15 billion was spent in unscheduled downtime, and things hadn't even been fixed yet. So the takeaway from this is that predictive maintenance can help reduce your unscheduled downtime. Scheduling downtime is far less expensive than scheduling than an unscheduled downtime, and there's no loss of revenue or loss of production to something that could have been prevented. So predictive maintenance will help you keep track of things pertaining to the drive, pertaining to equipment outside of the drive. And where it's especially helpful is in applications where a drive and motor have an irregular cycle. They don't run 24/7, so you don't really have an idea of how many hours a day it runs or when maintenance should be scheduled. And keeping track of these things in a plant and doing the maintenance when it's supposed to be done can get complicated. And if you do it too soon, you're going to be spending money unnecessarily. If you do it too late, you're going to shorten the life of the equipment. So some things that you need that we can keep track of: fans inside the drive. Some fans don't run when the drives are on, or run for some time after the drive is shut off. So actual drive runtime isn't a good gauge as to when the fans should be replaced. Relays in the I/O cards, they're not time dependent. They're a matter of actuations, how many times they've turned on and off. Personnel changeover, whether somebody has retired, left, if somebody's out on vacation, can mess up your maintenance schedule. And another question is, how is the maintenance schedule managed? Is it managed by the control system, or is it a spreadsheet on somebody's desk on a calendar? Or in some cases, Bob was the one who took care of that machine, and he knew when it needed to be lubed, and he knew when it needed to be cleaned. But Bob's retired 3 months ago. So in short, an accurate maintenance schedule is difficult, and it's a task that you all face every day. So there's several predictive maintenance parameters available in the 750. They can track runtime or cycles for some of the internal components on the drive, and also track runtime for your motor and machine, and let you know when it's time for bearings or lubrication. Now, none of that happens by magic. There's some data that you have to enter into the drive parameters in order for it to work. So I'm hoping that by now you're asking yourself, how do you get started with it? The predictive maintenance parameters can be configured either using the HIM, if you're connected to a Logix controller through Studio 5000 or Connected Components Workbench. That's free software, otherwise known as CCW. Predictive maintenance parameters are located in a folder called, not surprisingly, Predictive Maintenance, and it's under the Protection folder. I'll show you that a little bit later. When you're setting this up, you have a few choices of what happens when a predictive maintenance event occurs, and it's a configurable notification. We'll cover that in a little bit, but I just want to point out that you don't have to, you're not fixed to a specific action. But all the maintenance parameters can be read through a PLC, and you can bring it in either through data links, through explicit messages in the code, and then when the data, as the data gets collected, it can be disseminated to the relevant personnel. So what components do we keep track of? This table that I'm showing has a list of predictive maintenance items in the drive, and where they're used. Now, the cabinet fans that you see listed, the third item, replace the heatsink fans when you get to the frame 8 size drive. That would be about 350 horsepower normal duty at 480 volt. Specific application considerations have to be given some thought before you can input data into the predictive maintenance parameters. Things such as ambient temperature, air quality, how much vibration is the unit subjected to, and these things you need to think about and know before you go in and set up the environmental parameters. Once you've made those determinations and you've made those inputs to the drive, determining when you want to be notified is really a gut feel. We'll go through some calculations, or I'll show you in a spreadsheet how the parameters are all interrelated, but everything is going to be based on 100% mean time to fail. When you are setting up when you want to be notified, you're going to select 80% of life, 50% of life, and at that point, when you reach that event level, you'll need to determine what event action you need to take. So we're going to look now at what's involved in setting up the parameters for a heatsink fan, just as an example. So in this case, we'll be doing a heatsink fan for a flange mount drive. And as I spoke about a little bit earlier, we need to have decided on a few things, such as the ambient temperature. Now, keep in mind, because this is a heatsink fan, a flange mount drive, rather, the heatsink is outside of the enclosure. So you need to take into account not the temperature inside the enclosure, but the temperature that the heatsink is exposed to. And then again, dealing with the air quality, is it dusty, dirty, metal filings, those kinds of things, and vibration will help you. Knowing these things will help you determine what your D-rate factor is. And now you're saying, D-rate factor, what is that? D-rate factor is something that shortens or calculates the number less than 100% mean time to fail. So you can set it up for, it's a value of 0 to 1. And if you put in a 0.5, you'll derate the fan for 50% of its life. And then your event action is based on that value. The next slides will cover the 4 parameters that'll need to be configured, along with other read-only parameters used to monitor predictive maintenance. Now, I'm told that the user-configured parameters are shown in green, and the read-onlys are in gray. I'm colorblind, so I'm going to assume that I was told right, and it's not showing up as fuchsia or something on the screen. That was a joke. So we're going to start by setting a few parameters based on the environmental conditions where the drive's installed. Parameter 470 is set for the maximum ambient temperature around the drive. Now remember, the heatsink, it's a flange mount drive, so the heatsink is out the back of the enclosure. It should be set to the estimated temperature that the drive is going to see. In the case of a flange mounted drive, outside the cabinet, we're going to say in this example that the highest temperature that it's going to experience will be 40 degrees C. Now let's just say, for instance, the drive is, normally it's only like 30 degrees C out there, but there's a couple of weeks a year that we get up to 40. 40 degrees C is the value that you want to put in that parameter. Now here's where you get into the D-rate, heatsink fan D-rate parameter. As I had said, sorry, somebody was just texting, sorry. The D-rate is set based on the ambient conditions, meaning is it dirty, really, really hot, subjected to a lot of vibration. You can derate the fan from here. Here we go. Did that switch? Yes. Okay. By default, the D-rate factor is set to 1, so you're set to 100% of mean time to fail. If you've got a really dirty, dusty, environment, setting that to a 0.5, we'll adjust the point at which the event level is calculated down to 50%. And just as a point of reference, in here we're showing that in parameter 489, the expected life of the fan is 15,300 hours. Now that's the D-rated value. We said it was 0.5, so the mean time to fail for this fan is 30,600, just to be clear. Now that 30,000 hours, if you want to compile it by year, if a drive runs 24/7, 52 weeks a year, that's 8,736 hours a year. So you get quite a bit of life out of the heatsink fans. So the drive will keep track of the number of hours that the heatsink fan has been running in and it'll keep track of that in parameter 490. And the remaining life of the fan is then calculated. And this is where the math, get your pencils out. Remaining life of the fan is calculated by the difference between the total fan life, as was calculated on the previous slide, and the elapsed life. And then the remaining life is stored in parameter 491. Now, those are in gray, so those are only parameters that you can read. You can't alter those at all. In addition to just simply calculating the remaining life of the components, predictive maintenance can also trigger an event when the life has reached a certain level. We call that the event level, and that the event level parameter determines when the event is triggered as a percent of the total life, and is stored in parameter 491. All right. So if we were to go back, we said that parameter 489, we said was 15,300. We set the event level at 90%. So 90% of that 15,300 is the 13,370. And at that point, once the elapsed fan runtime has reached that 13,770, will trigger the event, and an alarm or a fault can be triggered. When we get to parameter 493, the event level action, this is what happens when you reach the event level. As a default, it's programmed, it's shipped out of the factory as ignore, so nothing will happen. You can program that for an alarm, which will allow the drive to operate normally, but it'll change a bit in the status word, the predictive maintenance status word. It'll change that bit from a 0 to a 1. And that can get read back to the PLC, either through the data links, or you can write an explicit message if necessary. You can have the drive create a minor fault, which will allow the drive to continue through the production process. And then once the drive stops, a minor fault will prevent the drive from starting again. Or you can create a major fault, in which case then the drive will fault in the middle of production, stop, and won't run again until you replace the fan. So now you've done all the right things. Your gut was right when you selected the 50% of life, and you replaced the fan in scheduled downtime. You've replaced it. Everything is good. But now you've got to reset that parameter so that you can get the life back to 0. This is accomplished by going into parameter 471, predictive maintenance enable, reset enable, I guess I should say, and parameter 472, which then you select which value you want to reset. Each of the items that we monitor, meaning the heat sink fan, the internal cooling fan, bearings, lubrication, all each have their own bits to reset. So if you just replace the fan, you go ahead and reset that one bit. If you've done the lube and you've done your bearings, reset those bits. You do them one at a time. So if that wasn't confusing enough, and I'm sure it was, here it is. What I've done here is created a spreadsheet that will allow you to see how the numbers interrelate. So here, in this example, let's put this back. Let's go back to the beginning. This is the status bit word that I was talking about, that can be read back to the PLC. And I know it's a bit of an eye chart here, but if you look, here's your heatsink fan, here's your internal cooling fan, here's your motor bearings, here's your motor lube, here's your machine machine bearings, and here's your machine loop. So they've all got their individual bits. So you can read each individual one back, or you can read as a word back, just getting that, I've got maintenance to be done. And as a default, the maintenance temperature is set to 50. Yes, that's high. This actually is set to 1, the fan D rate. I picked the 30,600 just because that was the number that we had in the presentation. And the event level is 80%. That was the default value also. And as default for the event action, that's 0. That was ignore. Okay. So now if we're going to follow what we set up for the flange mount heatsink fan, we said that the ambient temperature that the drive was going to see was 40 degrees C. And we said that the environment was pretty dirty or was subjected to considerable vibration. So we're going to set that to 50% life. So now your event level here, the value that we have set up for 80%, is not going to be based on the 30,000. It's going to be based on the derated value. Okay. So now if I run this to about 11,000 hours, I'm only at 71%, so nothing is happening yet. You can see this bit still hasn't changed. If I get this up to 13,000, now I'm up to 85%, and I've triggered the bit. So now this can be read back to the PLC, and you can be told, be warned that, hey, it's time to do some maintenance on the drive. Here's your reset. Parameter 471 is your reset enable. And 472 is are your choices for ready, heatsink fan, internal fan, and like I said, the other ones that are listed up there in the status word. The event action we talked about, 0 is ignore, 1 is alarm, 2 is a fault. So here is how you set those up, and those are your choices to what happens once you reach this 80%. And I hope that makes it a little bit clearer. Here I'm looking at a drive in CCW. And we'll go back to, as I said, we were in the protection folder, and then we went down to predictive maintenance. And here's are all the parameters that are listed in the predictive maintenance screen. Little cheat here. If you want to look at just the heatsink parameters, if you type in HS in the filter, it'll bring these up. So here's your total life, elapsed life, remaining life, event level, event action, and your D rate.
Okay.
Hope that makes a little more sense. In the programming manual for the drive, the 750 PM goes into a lot more detail about the parameters and their values. Using predictive maintenance with a Logix controller, Appendix B in the programming manual has a lot more detail about that. Hopefully you all have access to the Rockwell knowledge base as well. There's a lot of good information out there, and they have revamped the knowledge base, and the search function actually works pretty good. So if you haven't got access to the knowledge base, let me know. Shoot me an email or whatever, and I'll get you set up. Things that'll help you. The 750-PM programming manual, the 750 TD, the tech doc. There's also a really good white paper in literature library, PFlex WP002. I have those. If you don't want to go to download them from the literature library at Rockwell. There's a link for it there. Some good documentation for there. So here's the literature library link, the knowledge base link. Like I said, if you need help you don't have access to documents, let me know. We'll get you squared away. There's a link for the Turtle and Hughes webinars, the upcoming webinars. My email address, phone number, office phone number. And if you call the office, say hello to Alice. Our counter is open for pickups. We've made arrangements for no contact pickups. Just call the office, business as usual, and then you can go pick up your equipment. If you're like me, I'm going to be staying on the call for a little while. If you're like me, you'll hang up and then go, darn, I meant to ask that question. I'll be here, but you can also just email me or call me, and we'll take care of it. A couple of housekeeping things. Come August, we think it's going to be August now. We'll be hosting Drive headquarters, Linden, New Jersey, scheduled for the week of August 3rd, and we'll be doing it in Newburgh this year, the week of August 10th. If you think you might be interested in coming, shoot me an email, and we'll get you, make sure that you get registered for it. And that was it. I want to thank you for your time this morning. Stay safe. And like I said, I'll be hanging on the call for a while. So if you want to chat your messages, I can unmute microphones, and we'll take it from there. So thank you very much, everybody. Have a great day.
Thanks, Peter.